Okay, so let the party commence. Hello, everyone, and welcome to the first class of AVR, architecture, assembly, reverse engineering, whatever. In this series, I'm going to introduce to you my best friend for the past few months. It's the datasheet for the microcontroller that I guess many of you have or had an Arduino Uno board at some point. So we are going to talk about this microcontroller in the heart of the Uno board and many other boards. I will share my screen in a second, but I'm also going to share, thank you, Pratyush, for your comments on the chat. I'm also going to share a bunch of links during the session. So I've created this shared document where you will be able to just find the links that I share in real time. And you can also comment there if you have any suggestions or anything. And I'm also going to be monitoring the Zoom chat. So right, let's get started. I'm sharing my screen. I will just need an indication from you that you can actually see my screen. And then we can, where is the chat? Okay, where is the chat? Here it is. So as soon as you tell me that you can see my screen, we'll get this rolling. It's visible, thank you. Perfect, so, oh, embarrassing. That's my homepage. I'm not a unicorn. Anyway, so this is the document, and we are going to dive into this data sheet right away in a few minutes. But before we do, let me just introduce to you the environment we'll be using for the experiments. So this is Wokwi, an online Arduino simulation environment I've been working on, and that's why the datasheets and I are such good friends. We'll just get the Blink examples. I always like to start with Blink. Let's make the font size a bit larger. Let's say 24. And yeah, let's run it, and we can see the LED blinking. Fun. Let's remove all the comments. And just, okay. Yeah, just to get you familiar with this, basically we have the Arduino source code on the left side of the screen. And then we also have a file that defines which parts we have in the simulation. So in this case, we have an Arduino Uno, a resistor, and an LED. And then there is another section that defines the wiring, the connection. So Uno pin ground is connected to the cathode of the LED. That's the black connection. And we have two more blue connections defined here. And we are not really going to spend time writing new diagrams or changing the wiring. I just wanted to let you know that this is how it's defined. But this time we're in this session, we are, and probably in all the other sessions, we are just going to focus on the code. So I asked you to do some homework and get yourself familiar with, first of all, let me share the link. So if any of you want to go to the Blink demo, this is the link. So I asked you to go over some bitwise stuff, and I will do a really quick rehearsal of like how to do bitwise stuff in Arduino, just show you a few tricks that can be useful. So first of all, let's set up a serial console, and let's print there. So if you want to type a number in binary in Arduino, there are like a few ways. You can just 0B and then the sequence of bits. So for instance, let's do 1000 and 1000. And then if we run this code, this will actually print the decimal value of this binary number. Let's do this. So 136, that's the decimal code. And we can go the other way around. If you wanted to print the binary value of 136, we could just give serial.println a second value and tell it to print it in binary. And we got the binary result right here. So these are like just a few useful utilities. One more utility that I really like is the bit macro. So if we want like to set a specific bit, let's say the most significant bit, the 7th bit, we just write bit 7, and that would return a number with the 7th, actually the 8th from the right, the most significant bit set. And then we can go ahead and change it, like add a few more bits, like bit number 1, which is the second bit because we start with 0, the second bit from the right. And basically, these macros are useful, and we'll use them a lot today. And if you're still like having any questions about bitwise operations and how to use them in Arduino, feel free to ask after in the office hours. And we have 3 assistants here, Bo, Jake, and I think Alexander is the third one, right? Yeah. Thank you, Bo, for the comment. So that was a really quick overview of like a few utilities that we can use to work with bit in Arduino. There are a few more like bit set, bit clear, bit read, and we might meet them in a few moments. And now that we covered that, I want to show you an interesting example. So this is a short program. I will also share the link if you want to play with it yourself. This program actually does something very simple. It sets up the serial console, and then it prints okay, and then it prints the address of this variable. So we have a variable, and it prints the address of the setup function. And I'm going to run it, and while I'm running it, observe the results. So apparently, it seems like both this variable var1 and setup they occupy the same memory location. Now, usually that wouldn't really be possible. Like there is a memory location and it can contain one thing. So how comes both the variable and the setup function have the same memory address? And by the way, if I change this value a bit, like let's 119, so you can see that var1 moves a bit above. So it's actually the real address of var1. So how could it be? And I think this is the first interesting thing about AVR, and we can find it in the section. Let me just move away the participant list. Okay, about the memory section. And as soon as we open the memory section in the datasheet, and actually, you know what? Let me paste the link to this datasheet. So you all have it. Just a moment. This is the link. AVR AT. If you want to check it out, this is the datasheet. You can see that the AVR architecture actually has 2 main memory spaces, the data memory and the program memory spaces. So basically there are like 2 sets of memory addresses, and they are separate. And that's something that is not very common if you are used to other platforms such as x86 like Intel or ARM. They have one address space with everything, with the code and the data. But no, AVR is different. You have a different set of a different space of addresses for the variables and the data. and another set for the code. And that's the reason why the var1 and the setup had the same address. Like it's the same address, but it's a different address space. And if we want to be accurate, actually the datasheet also mentioned that there is a third address space for the EEPROM memory. And we are not going to bother with it right now, but there are like 3 memory addresses, 3 spaces, different spaces of addresses. And then it goes in depth to describe the memory, and we can see that the program memory starts at this address, and actually, yeah, this is for the 32.8. So the program memory starts at this address and ends at this address, and then this is this is for the for our chip. Like this is the start address, and this is the end address. But if we check out the second address space, the data memory, it's actually a bit more interesting. And we can see that it has a few sections. So the program memory is pretty simple, one address space with the code of the program from the flash. But the data memory, it has like these registers, which we will get to when we dive into assembly. And then it has that I/O registers. And you can see that there are like 64 I/O registers, and then there are a few extended I/O registers. And these I/O registers let us control the peripherals, like the GPIO ports and things that are part of the microcontroller. So I2C, UART, SPI, they are all controlled by writing and reading from these addresses, either these ones or these ones. And for now, there isn't a big difference for you between the standard and the extended I/O registers. When we get to assembly, there will be a difference. And we also have another sort of address space, which is the I/O address space. I'm not going to talk about it today, but when we get to assembly, we'll have to recognize that it exists. And finally, after the registers and the I/O registers, we also have the SRAM memory, which is where we store our variable. So that's why all the variables that we have will always have this address of 100 hexa and above. If we declare a variable, it will always get an address between this value and that value, which is the maximum for the chip that we are working with would be 32.8. So that was like a quick overview about the memories that we have, the program memory and the data memory. And I think the important takeaway is to remember that they are 2 distinct things. And when we are asking to read data, we should tell the microcontroller if we want to read from the memory or from the program address space. When we write, it's pretty simple because we can only write to the data space and not to the program space. With that, let's start exploring how we can interface with the actual hardware. So as I mentioned, there are like these I/O registers, and they let us control the hardware. And the first piece of hardware that we are going to control is the GPIO ports. So these are like the pins that you have on your Arduino Uno. And if we go to the section that talks about the pin configurations, it shows us the layout of the chip. This is the layout of the chip. And you can see like it has all those different pins called PC0, PC1, PB1, PB5, etc. And if you are used to working with Arduino Uno, you are probably just used to pins 0 to 13 and A0 to A5. And the quick way to know which is just to Google images Arduino Uno pinout, and like there are many guides like this one. So you can find a bunch of images that show you the pins. But usually you get, open a new tab, usually you get used to it really quick. Yeah, usually you get used to it real quick. Basically, all the analog pins are just PC0 to PC5, and then the digital pins are PT0 to PD8 to PD7. So starting with PD, and then let's remove this window. And then the remaining few are PB0 to PB5. So you just need to remember that these are their names when you are working with the microcontroller, not with the Arduino environment. And Arduino itself takes care of the mapping. I think I actually have the code here. So if we have time, we can take a look at it during the office hours and see how this pin mapping happens in the Arduino runtime library. Anyways, getting back to the pins. So we now know how to map between Arduino pin numbers and those PC1, PC2. And let's see, we have this LED. It's connected to pin number 13. And according to this pinout, pin number 13 is actually PB5. So what we are going to do, we are going to, instead of using the Arduino functions, we do need this one. Instead of using the Arduino functions to control this pin, we are going to use the GPIO registers. Just write to the registers and turn the LED on and off. And in order to do that, we will open the section of that talks about the IO ports. And if you will probably recognize soon that there is a pattern. Each section starts with like an overview or a description of that peripheral, in this case, the GPIO, then some specific section depending on the specific peripheral, but it always ends with register description. So it tells us which registers we have available to work with. So in this case, we can see that we have, for each of the ports, PB, PC, and PD, port B, port C, and port D, we have 3 registers, the port data register, data direction register, and input pin address. So there is a set of these 3 registers for port B, for port C, and for port D. And what we basically want to do, we want to set one of the pins to high. But before we can set it to high or low, we need to also set its pin mode to output. So what is the equivalent of this code in this GPIO length? To get an answer for that, we actually need to read the text and not just look at the registers, even though sometimes just by looking at the registers, you can get a pretty good understanding of how you would do things. And there is a lot of data here, but I think this is where they start to explain how things work. So you can see that if we want to configure the pin, then we have to use the DDXN. So DDR DDR-A, DDR-B, C, or D, to select the direction of the pin. If we are writing logic 1, so if the DDX and the bit, when we look at the register, we'll see this DD, like they call the bits DD0 to DDC0 to DDC7. So if it's written 1, then the pin is configured as output. If it's written 0, the pin is configured as input. So in our case, let's write it down. We want to configure PD, that was PB5, that was pin 13. We used the mapping and we saw it's PB5. So we want to configure PB5 as output. And we can do it as the datasheet suggested by setting DDRB and just setting bit number 5. So let's try that. And we can see our code still works. If we remove that, then actually the LED still blinks because of the pull-up register. And you can't really see the difference in the simulation right now. But this is the equivalent of this code. And now let's replace these digital writes with port like writing to registers. So we can see that if port whatever is written logic 1 when the pin is configured as output pin, it's driven high. If it's written logic 0 when the pin is configured as output, then the pin is driven low. So basically, we just need to toggle this port register. So we could write, instead of this, we can write port B. So bit set, we want to set bit number 5. And then to toggle it low, we would like to just clear that bit, unset it. And again, these are like just helper macros. And we can see that we get the same behavior. So now we blink the LED. Instead of 5, we could have also used like those like they have constants. So we can say port B5, and that's basically equals to 5. But usually I just write 5 instead of using these constants because it's shorter and I think it's clear enough. And by the way, we could have also written it like this way instead of using the macros. That's what these macros expand to. So basically, that would be the equivalent of what we had, but I think the macros are much more easy to follow and understand. So I usually use them when I work with Arduino. And these are Arduino specific macros. If you work with the AVRC compiler toolchain, then you obviously can't use them. And then there is another interesting bit of information. It says that writing logic 1 to pin xn toggles the value of port xn independent of the value of DDR. So instead of like setting it to high, then setting it to low, we can just, so if we just do it like that, it will always be on. But if we write to bit number 5 of the pin B register, as the datasheet said, it will actually toggle the pin. So it turns out that using the direct register access actually produces shorter code in comparison with just using digital write and pin mode. And to make it more fun, let's look what happens when we connect LEDs to all these pins. So pin 0 to pin 7, these all are, where was that? Yep. Pin 0 through pin 7, they are like PD0 to PD7. And usually if we wanted to use the Arduino digital write API to control these pins, we would have to write a loop. So right now I have like this code that toggles that specific pin number 1. But if we work directly with the registers, we can just say something like this. port B, so port D, because these are PD0 to PD7, is just all ones, or maybe this will even be a bit clearer. Just set all the pins to output, and then we can say just toggle. We still need the delay though. We can just, DDR to set the data direction. And then we can just, like we did it before, write to the pin register to toggle all those pins at once. Let's see that. So isn't it amazing controlling 8 different LEDs in just like a few lines of code? We can do other fun things like using bit shifts to, use to create sliding patterns and stuff like that. But the thing is, this is how you would normally write code to interface with the GPIO pins if you didn't have the Arduino library that provides all these abstractions. If we check out the source code for the Arduino library, we'll see that they are using these exact registers behind the scenes. So let me also share the link to this setup if you want to take a look. Yep, somebody added some useful information. 8 LEDs on port D. Okay, so this is the link if you want to check it out. Okay. And one more fun experiment. So we worked with the output pins, and that's when we set DDR to 1. We know we set a pin to output, but we can also set it to input. And let's go back to the section about the registers. So So yeah, so we use like all these 3 registers, like port B, just to write. I clicked the wrong link. So let's go to the last one. So so port D to write to the to control these 8 pins, and then to set them high or low, DDRD to set the direction, and then we used pin. It actually says input pins, but we used it to toggle. So it also mentioned that here, writing to the pin register provides toggle functionality for the I/O. Juan, thanks for sharing the link for the core library. Let me just add it to the document. AVR core GitHub repo to do. Oh, nice. Somebody added a to do with the link. So I will do it. So there we go. We have the link here. So yeah, let's see what happens when we try to use these as input. So I have another demo here with this time with the 8 switches that are connected to the pins. And normally, I wouldn't be able to use those two if I enabled serial output. In the simulator, it would work, but normally it wouldn't. So instead, I connected a small LCD screen, so we can just print output to this LCD screen. And in this case, we are going to set all these pins as input. So basically, we need to write to DDRD, we need to write there 0 for all the pins, so to set them as input. But if you remember, when we read from a button, we usually need a pull-up resistor, and we don't have any pull-up resistors in these schematics. So we want to enable the pull-up resistors for those pins. And for that, if we go back to the description somewhere, you can see that so if port XN is written logic 1 when the pin is configured as digital input pin, like we are doing now, the pull-up resistor is activated. So writing 0 deactivates the switch the pull-up resistor off. So basically, in order to enable the pull-up, that was this one. Let me also put the link in the document. So that's switches, 8 switches. Okay. So in order to set up the data register, the pull-up resistors, we just need to write to port D and tell it to enable it for set all the bits to 1 to enable it to for all these pins. And now all we need to do, we just we can just lcd.clear. Let's actually, okay, let's start this way. lcd.clear and then lcd.print, and we can print the value of pin D, sorry. We said that pin is the port input register. It lets us read from the port or toggle it in output mode. And we want to print it as binary. Oh, I need to disable notifications. Yeah, so we can see it's quite interesting because we run this continuously. So we run this continuously. So we clear the screen repeatedly, and what we want to do, we just want to print it if the value has changed. So let's store byte value, and then we can say value byte new value equals pin D, and then if new value doesn't equal to the existing value, then we only print it, and then value equals to new value. So just so we can see the output, and let's just set it to some random value initially. So yeah, and so yeah, you can see those. Yeah, for some reason, yeah, I set it. So yeah, I need to print a new value and not the value. Now it will be correct. So yeah, you can see it prints all once, and if I start toggling these pins, it will actually flip the bit when one of these switches is closed, like the circuit is closed. So yeah, so that's how it works, and you can play with it. By the way, using bin isn't the perfect solution here because it won't print any leading zeros. So if I switch this one, it will actually disappear. There should have been a 0, but it doesn't print leading zeros. So, the leftmost zeros just disappear. So we could have written a short for loop that would print the all the bits nevertheless, but I think just for the demo purposes, this is fine. So I just wanted you to know on this limitation of using the print with bin. Okay, so that was like a quick tour of the GPIO registers. And what I want you to take away from here is not just like, okay, we now know how to work with those registers, but I want you to start getting comfortable with reading this data sheet. And, it takes time. I mean, I knew where to look because I read it before. What I usually do, I just, read the entire section once, then look at the registers. Only then I start to, go back and forth like I did now. And before we, somebody asked if there is a way to get leading zeros. Not that I'm aware of. I guess there could be some. No, I don't have anything that comes to my mind. Let's close this. We don't need this anymore. Neither this. Nothing that comes to my mind right now. So you probably have to do it manually or use some external library. Um, Before we part ways with the GPIOs, one more thing to show you. So this register description is like super common. You will find it in every section, and it has a very specific format. So you see the name of the register, quick description, then all the bits, and each bit has a name, and this name is actually a constant that equals to the index of the bit. So port B4 just equals 4. And the register itself, you can see like for each of the bits, if it's read, write, or both. In most cases, the bits will be read write unless they don't have a specific function. And some cases like this one, it doesn't have a specific function. And you can also see the initial value of the pin. And usually almost every time, almost always it's 0, but there are a very few cases, I think, in the I2C registers that they actually start with the value of 1. And one last thing to know about the registers, there is like these two numbers. And this is the first time we meet the IO address space. So this is the IO address space address of the memory, and this is the data address space. So this is the address that you will normally use, the one in the parentheses. I fell for it multiple times, and we can, verify it if, let's just take this demo and serial begin, serial println. So let's print the address of port B as hexadecimal. And build failed. Yeah, we need to typecast it so it will be happy. And yeah, you can see it's 25 hexa, just like the datasheet says. So this constant is actually equals to 25 hexa. This is how it works. So that's all about the GPIOs. Now, actually, there is the next thing we will talk about also has something to do with the GPIOs. We are going to talk about interrupts, and interrupts are basically the way of the processor, the microcontroller, to let us know that something has happened. And we can see the list of all these supported interrupts somewhere. Actually don't remember where it is. I usually just search for vectors. Let's see if I can spot it real quick, or interrupts. Yep, very useful. So yeah, that's our chip. And we can see like these are like all the interrupts that this chip can generate. And right now we are not going to talk about how to handle interrupts in non-Arduino environment, or when we get to assembly, we'll probably mention that. And instead, I'm going to show you two ways to do this within Arduino. So let's go back to the switches. And inside Uno, there are actually two external pin interrupts. So the two interrupts that can be dispatched whenever a specific pin is changed, int0 and int1. And if we go back to the pin descriptions, we can see which pins they or pin configuration. We can see the pins they belong to. So you can see that int0 is for PD2, so that's pin 2 of the Arduino, and int1 is for PD3. And in order to listen to them, we can just do something like that. Let's just set up serial printing anyway. We are not going to use 0 and 1 anyway, so it doesn't matter right now. And I'm going to use the attach interrupt method and call pin, I don't remember the name of that function. We can actually write, yeah, I think it was digital pin to interrupt number. Let's just Google that very quick. Digital pin to interrupt. Okay, so that would attach to int0 because this belongs to that pin, and then we need to give it an address of a function. Let's call it interrupted, and then interrupted. And then we need to tell it when to call the interrupt. So for instance, on the rising edge. So whenever this pin goes from low to high. And in interrupted, we can just print, I was interrupted. Let's run this. And we can see that as soon as I click the switch that is connected to pin number 2, it was interrupted. Now, if I switched off, it doesn't really matter because we asked to be notified on the rising edge, and that's the falling edge. But then whenever it goes on, or in this case, whenever the circuit is open and the pin goes high, we get the interrupt. And that was like the Arduino-ish way to define this interrupt handler. And now I'm going to show you how to do it via registers, how to enable this interrupt and act upon this interrupt. So if we go back to this section, there is like a section about external interrupts. So int0 and int1, those interrupts that are associated with the pins are external interrupts. And if we wanted to enable them, we would need to check out the external interrupt section. And there are two kinds of external interrupts. In this case, we are interested in the kind that controls int0 and int1. And we can see that there are like two registers that control the external interrupts. There is control register A, and there is interrupt mask register. So we can say that EIMSK let us enable interrupt request 0 and interrupt request 1, or int0 and int1. So if we want to enable this interrupt, we want this interrupt to happen, we need to set this bit to 1. So let's do that. Let's go ahead and set it up. That was the porty switches. So instead of doing it the Arduino way, let's say bit set. And we can either write 0 here, like the index, or we can just, use this constant int0. So that would enable the interrupt, but only enable it. We also had this rising parameter. So how do we set that? And for that, we would need to look at the second register, the EICRA, external interrupt control register. And we can set it to decide when this interrupt fires. So we basically, actually, we can just do it with assignment because I think we'll need multiple bits. We want it to go on the, so that's int0. We want it to go on the rising edge of int0. So we need to set those two bits to 1. IST00 and IST01. And again, we could just use their indices 0 and 1, but in this case, I think it's better to use the constant. So it's easy to figure out what these bits actually mean. And now we are almost done. We configured the external interrupts. The only thing we need to do is to declare the function that handles these interrupts. And for that, we would need to use something called a macro that will define an ISR, an interrupt service routine. And there is some convention, I think, for it's the name of the interrupt _vect. And that would tell the compiler to put the address of this function that we defined here inside like the memory address specified in this table. So it will just put it here inside address number 2, where int zero handler lives. Okay, let's restart the simulation and see if this works with registers. Okay, and then as soon as I toggle this pin, we can see that it's basically the equivalent. And if we just, let's do this finally. Let's go to the Arduino library and look at the source code for attach interrupt. If we check out the source code for attach interrupt, we can find it here. And there is basically a very big switch case that depends on the pin number and which processor we are running on. But you can see that it sets basically those two registers like we did, like EICRA and EIMSK. On some other processor, like the register names are quite a bit different. But basically, it does the same things like we do, just setting up those two registers to enable the interrupt. So that's it. The Arduino library is just like, most of the time, is just like reading and writing the right registers for us, like we did here. Before we move on, I want to introduce to you to two more functions. Let's say we don't want interrupts, any kind of interrupts. There is a function called CLI that will simply clear interrupts. Oh, Andreas is asking, don't we need to enable global interrupt? So when Arduino starts, it already sets up interrupts for us. So it enables the interrupts. And CLI does the opposite. We are going to disable the interrupts. So if I call this in my setup and I run the code, we will notice a few things. First of all, the interrupt doesn't get fired anymore. We don't see the prints. And second, the LCD stops updating. So probably the LCD somehow also depends on interrupts. And that would be fixed if I re-enabled interrupts at some point. So now I clear them, set some flags, and then re-enable them. And we can see that the interrupt, everything is working as normal. Now, disabling interrupts is usually something that you don't want to do unless you need a precise timing, or you want to write to a few registers and make sure that nothing happens in the middle. Like in this case, if I enable this interrupt, but I don't set the condition, it could like fire before I have this assignment done, because the previous condition was met. So it makes sense to, first of all, disable the interrupts and then set this up. And I want to show you something, another thing, what happens when I disable interrupt. So let's dump this down to a very simple program. Serial begin, serial println hello. So hello Hackaday. So this runs, prints hello Hackaday, and we are all happy. But if I disable interrupts, even after calling serial println, we'll see that it's just printed hey. And the reason for that, the serial library depends on interrupts to know when to send the next character. So if we disable the interrupts, we basically kill the serial. Not only that, let's see, let's try something else. Hello, and then print the other one after 1 second. So we have hello Hackaday after 1 second, and we can see it prints hello. Let's restart it. It's print clan. Yeah. So it prints There is some issue with the simulation. It doesn't clear the output when it begins. Let's restart it. Hello, and say 1 second after, Hackaday. And we can even change it to 5 seconds to make this more apparent. Hello, and then after a short while, it will print Hackaday. But then see what happens if I disable interrupts while I'm calling delay. So I'm disabling it, calling delay, and enabling it again so I can see the output of the prints. And see what happens. It didn't delay. So delay also depends on interrupts. And if at some point you disable interrupts and then call delay, then delay is not going to delay at all. So that's one important thing to know. Disabling the interrupts for more than a few commands will probably get you very unpredictable results. Delay is not working, serial println does not print. So you want to use this CLI tool, clear interrupts command, sparingly. You don't want to use it too much. So that's all about interrupts. And Christina, I would appreciate if you write in the chat how much time we have left, because I want to okay, I will answer that question that we have from Paulson later in the Q&A session. Okay, so we have about 5 minutes left, and that would be a good time to briefly talk about timers. So in AVR, timers, they basically let us interact with or count timers, the time. And we can see that we have, where is the timer? We have like 3 timers, timer 0, timer 1, and timer 2. Now, before we get into, and we won't like finish this today, we'll continue talking about timers next time because they are really complex. In fact, they are the most complex peripheral that exists on the AVR. They are more complex than anything in AVR. And basically, you can figure it out only by looking at, so this is timer number 1. And if we take a look at the register description, we can see like it has 16.11.1, and it goes down all the way to, yeah, you can see how many different registers it had. It had like 9 different registers, and it has like so many different modes of operation and whatnot. So if we wanted to cover timers, we would have to dedicate, like cover them end to end. We would probably have to dedicate 5 sessions just for that. So we are not going to do that in this course, but I'm going to give you a little taste. And what I'm going to do, I'm going to set up a simple program that will sort of simulate this blink. Let's open blink again. We have it here. Simulate blink using timers. So I won't go into all the details because you can find them in the datasheet. But what I will do, so we have this delay here, and I'm going to replace this delay, or you know what, the entire loop with timer that will do this for me. So basically, we are going to use this TCCR1, and we are going to configure the timer so that it counts 1. It goes up by 1 every where is that table? Yeah, every 256 clock cycles. So a clock cycle is basically you know this chip runs at 16 megahertz. So a clock cycles is 1 divided by 16 million of a second. There are 16 million clock cycles in a second. So every 256 clock cycles, the timer will go up by 1. So we can say the control register A will just set it to 0 because we are not interested in any of the configuration options there, and you can check them up later. But for the second control register of the timer, we actually want to set it to this value. So to set it to count every 256 cycles. So we want to enable this speed, count every 256 cycles. And now we want to define a function that will be called whenever this timer overflows. So this timer counts 16 bits, so from 0 to 65,535. And we want, whenever it overflows, whenever it gets to the top, we want to call a function to declare an interrupt that will be called. So we define an interrupt that is called timer 1, because this is timer 1 overflow vect. And whenever this happens, just toggle the pin. And if you will multiply this number by that number, you will see it's roughly equals 16 million. And that's the number of cycles in a second. So we basically, whenever it overflows, we know that 1 second passed more or less. And before, if we run it, it won't do anything right now because we can remove these serial prints. It won't do anything interesting right now because we have set up the counter to count, but we haven't set up the interrupt. And to enable that, we just need to enable the interrupt bit, similar to what we did with the GPIO pins. This register controls the interrupts for the timer, and i.e. Timer overflow interrupt enable. We enable this overflow interrupt. Let's run it. And we can see the LED is blinking roughly once a second. So this was like a real quick introduction to using the timer to count clock cycles. And I think now is a good time to move on to the Q&A session. And for the timers, we still have some more things to learn about them. So I hope you will join for the next class where we will dive into the timers. And then after going more deeply into timers, we'll start talking about the assembly language of the AVR.